So today we are going to start talking about finding the inverse for a function. Before we do that though, let's just review briefly about what a polynomial is, how that leads the idea into functions, and how that will start to develop our idea for inverses. Right? So remember, a polynomial. Right? A polynomial is some type of statement where all of your variables could have, let's say, positive integers as their exponents. Right? So for instance, a 3x to the 19th plus 2x to the 11th minus 5x cubed is a polynomial. Right? And it's a polynomial because all of these exponents happen to be nice positive integers. Right? Note that we don't care at all about these coefficients out front. They could be fractions, decimals, positives, negatives, it doesn't matter. But in order to be a polynomial, then what we have to focus on are these particular exponents. Okay? So for instance, if I had a 5 minus 4x cubed plus a 2x squared, yeah, that's a polynomial. Right? If I had 27 minus, well, I don't know, how about 11x to the 4th plus 5x to the 22, yep, that's a polynomial as well. But as soon as those exponents start to become numbers which are not positive integers, then we start running into problems. For instance, if I had 3 plus 2x to the minus 4, right? As soon as we see that minus 4 right there, we know that, nope, that's not going to give me a polynomial. Right? Or if I had 9 plus the square root of x, I know I'm in trouble there because remember the square root of x is the same thing as the 1/2 power. Right? So that 1/2 power right there just shoots it all down, and no, that can't be a polynomial. Right? So again, a polynomial is one of these statements to where we have nice positive integers as my exponents. Okay? Now, where that can lead us to next is the idea of what happens when we have one of these statements and we want to call it an equation. Well, all an equation is a statement that has an equal sign in it. So, for instance, a 2x to the 3rd minus a 3x to the 4th equals 12. Right? That's an equation because of the equal sign in there. Right? Or maybe a 4x to the 2/3 plus 3x to the minus 2 equals 96. That is an equation because of the equal sign, but it's no longer a polynomial because of those strange exponents that we have up there. So again, all an equation is a statement that has an equal sign in it. So for instance, let's say Bob equals cat. That's an equation. A little bit odd, but it's still just an equation. All right. So where we can go next with all of this then is we've talked about polynomials and equations. What happens if our equations have certain properties in it that we can use to our advantage, right? And those properties can lead us into something that's called functions, right? And remember the idea behind functions is that we have some equation that we're dealing with here, like f of x equals 0 maybe. And what we're going to do is we're going to throw some values into that equation. The values that we plug into it, if you remember, are the domain values, and the numbers that pop out, those are my range values. Right? Some books will call the domain values the independent values, and the range would then be the dependent values. Right? So a lot of times these are the x's, a lot of times these are just the y's, but honestly, these are the values that we plug in, and these are the values that come out. Right? So what we'll have is the set of values over here in the domain that we're going to plug into some type of a function f, and we're going to have some answers pop out. For instance, maybe I'll plug the number 1 into this thing, and maybe the number 5 is going to pop out. Or maybe I'll plug the variable a in there, and that'll map over here to maybe a squared. Just depends on the function that you've got. But in order to be a function, every domain value, right, if you remember, has to get mapped onto exactly one range value. All right, so again, it's exactly one range value. All right, so let's think about our picture again. we've got our set of domain values here. We've got our set of range values right there. And we have some type of a function which is mapping that set of domain values into these range values. In order to be a function, every one of these domain values has to get plugged into my function and pop out exactly one range value. Right? So maybe it'll crisscross a little bit here and there, but that's the idea. Right? As soon as you have something that's different, it's not going to be a function anymore. So let's say I've got this point right here that I plug into my function, and it actually generates two different range values. That's not good. Right? Or maybe this point right here, that when you plug it in, generates three different range values. Right? That's where we're no longer going to be a function. Right? So again, every domain value goes to exactly one range value. So here's an example. Right? If we think about this particular function, or rather this particular equation, how about x squared plus y squared equals 9? Right? That's just our circle, right? That's centered at the origin with a radius of 3. Right? All right, so what I can do is, if you make a little xy chart right here, if you notice, if I let x be 0, then y could be 3, and that'll still make that a true statement. Or if x is 0, y could be negative 3, and that's still a true statement. So those are 2 points that are on my graph. So in other words, this single value of 0 in my domain gets mapped onto these two values in my range. Okay? Which means this equation is not a function. It's still an equation, but it's not a function. Right? And this is why you've probably heard of that vertical line test and why it fails. Right? So there's my equation, x squared plus y squared equals 9. Right? You can see if we just draw a vertical line all the way down through 0 right there, we actually hit my function 2 times. Once at this point 0, negative 3, and once at this point 0, 3. That is why the vertical line test can tell me if I have a function or not. If a vertical line ever hits the function in more than one spot, hits the equation in more than one spot, then it's not a function. So consider the parabola, just this basic parabola, this y equals x squared type of a thing. Right? You can see that, again, no matter where I draw my vertical line, I only hit the function in exactly one spot, or hit the equation in exactly one spot, which means this is going to be a function. And why is that? Because if you look at every domain value that we've got here, it does go to exactly one range value. Okay. All right, so now that's going to start leading us into the idea of finding inverses. So if I did give you a function, how do you know if that function actually has an inverse or not? Right? So before we delve into that, let's actually start asking ourselves, what does an inverse do? Well, if you remember, the idea of a function is it really is some type of a machine, right? So I think I've drawn this really terrible picture for you guys before, right? To where this is my function f of x, right? What we do is we take all of our domain values, plug them into my function, and out pops all of the range values. Okay? What an inverse does, it literally undoes all of this work. So if I call this f with a -1 on there, note that the -1 on there, it's not talking about an exponent. That's just a little symbol to represent the inverse of the function. Right? So f to the -1 of x like this, right? That represents the inverse of f of x. Right? So if we go back to the idea of a function, let's say I had the point 3 and I plug that into my function and then out popped a 9. Right? The way we could write that out is f of 3 equals 9. I plugged 3 into my function and 9 popped out. What the inverse does, it does the opposite of that. What it would do is it would take this 9 and then go backwards and have the 3 pop out. So in other words, f inverse of 9 would give me 3. So when I plugged that 3 into my function, the 9 popped out. What the inverse does, it undoes does or undoes all of those steps and puts me right back where I started, right? So in other words, I have this 3, I plug it into my function to get to 9, and then what the inverse does, it takes the 9, undoes everything, and puts me right back there at 3. So again, the inverse, we're not canceling off f's or doing anything like that. We're literally just doing the steps in reverse to get back to where we started. So what we could do is then start messing around a little bit. If I told you f of 4 gives me a 6, then what could we say about f inverse of 6? Right? What's that going to equal? Right? Well, again, if you think about it, if I had that number 4, plug it into my function f, 6 pops out. Right? So if I take 6 and plug that into my inverse, then what should pop out? Yeah, that number 4. Okay, so let's start thinking about how we can tell if these two things can actually match up with each other. In other words, if I gave you a function, does it necessarily have an inverse? And then if it does have an inverse, what's it going to be? So here's what we're going to ask. If we have a function f of x, 1, does it have an inverse? And then 2, if so, how do we find it? So let's go through these things one at a time. Right? So first of all, when does f of x have an inverse? You've probably done some of these before. You may remember, you may not. But the idea we used before was we would just switch our x's and y's to see what the inverse was going to be. Okay? Well, if f of x, mind you, if f of x here is a function, right, then the inverse itself is also going to have to be a function. Right? So in order to be a function, we have to have certain restrictions with our domains in order to generate these different range values, right? Because again, every domain value has to have exactly one range value. So we have to be able to have a picture, a graph, where the function f of x has one range for every domain value, and and the inverse will also have one domain for every range. So if you think about what we had said before, look at this function f of x equals x squared. Right? There are a few points that we have on our graph here. If you look at this parabola and those points, you can see just from the picture that it is going to be a function, right? Because it does pass that vertical line test every place. So if I drew a vertical line here, here, it doesn't matter where I draw that vertical line, it's going to pass. So what that tells me is that, yes, definitely, this is a function. Okay? So since this is a function, and we're trying to find the inverse, again, we've talked before about how we can just switch our x's and y's. What happens if we switch our x's and y's? Then what's going to pop out? What picture is going to pop out here? All right, so let's look at each of these points. Look at this point 0, 0, first of all. If we switch those x and y values, well, we still get 0, 0, right? So that's this point right here. Right? What about this point 1, 1? Same thing. If we switch the 1 with the 1, we still get the point 1, 1, which generates that point right there. If we look at this point 2, 4, and switch the x's and the y's, we get the point 4, 2, which is right here. And then we can do the same thing for these other points, right? For instance, negative 1, 1, if we flip those around, we get 1, negative 1. And then if I take this point negative 2, 4 and flip it, I get 4, negative 2. Right? So if we just switch each of those x's with those y values, this parabola that opens up now becomes that parabola which opens to the right. Okay? So the picture is easy enough to see, but then my question for you all would be, is this picture that we've actually drawn now a function? Right? And if you look at it, the answer is pretty obviously no. All right, so why is this actually not a function? Well, remember the idea of the vertical line test. If I just draw a vertical line somewhere on here, it's going to fail all over the place. Right? So unfortunately, what that tells me is that this function f of x equals x squared, right? When we switch our x's and y's, what we now have is actually not a function. Okay? So our goal here is this. What we need to have here is for f of x and for f inverse to actually be functions. Right? And here's how we can pretty much guarantee that's going to happen. Right? We know that in order for f of x to be a function, so let's look at, how about f of x equals x cubed. Right? So there's f of x equals x cubed. In order for a function to be, in order for an equation to be a function, it has to pass the vertical line test, right? So for f of x, that needs to pass the vertical line test, right, to be a function. Now, when we switch our x's and y's when we're finding the inverse, what we're going to need then is, if we're switching the x's and y's, we're switching our domains and ranges, so we don't want that vertical line anymore. What we need is a horizontal line. So in other words, if I gave you a picture here, in order to know that it actually has an inverse, what we have to do first of all is do this vertical line test to make sure that the original equation is a function. And then let's do the horizontal line test to see if the inverse will actually be a function. Okay? And this is why the parabola fails for us. If you look at the parabola again, it looks like this thing, right? Where clearly it passes that vertical line test every place, but it does fail the horizontal line test all over the place. Right? So what we know is this. Since f of x passes the horizontal line test, it is a function. However, since it fails the horizontal line test, the inverse is not a function. And I just realized, and I can't go back and fix it, but since it passes the vertical line test, f of x is a function. However, since it fails the horizontal line test, the inverse is actually not a function. Okay? So in order for us to guarantee our function to have an inverse, it has to pass the vertical line test and it has to pass the horizontal line test. The vertical line test says, again, f of x is a function. Horizontal line test tells us if the inverse is going to be a function. Right? What this means is that we want a function that is one-to-one. Right? What it means to be one-to-one is that every x value has a unique y value. Okay? And the key word here is unique, because if you go back to y equals x squared and made their xy chart, and you did the little picture, you would see that every domain value goes to exactly one range value, but sometimes those range values repeat. Right? For instance, again, we're here f of x equals x squared. If I plug in 1, I get 1. But if I plug in -1, I also get 1. Right? That's still okay in terms of being a function, but not for the one-to-one part. The one-to-one part would say that every single item that appears over in this chart, every single item that pops out, it must be unique. They must be different in order for this to be one-to-one. Right? And this is why the idea for the parabola does not have an inverse, right? Because it doesn't pass this particular test, which means it's not one-to-one, which means it's not going to pass the horizontal line test, so it does not have an inverse. Okay? Now, what we can do is sometimes we can restrict our domain for certain problems. For instance, again, here's my equation for x squared. We've seen before, it passes the vertical line test, so it's a function, fails the horizontal line test, so it's not one-to-one, which means it does not have an inverse. Okay? But what we can do is we can restrict our domain. Right now, the domain uses all of the real numbers, right? So everything from -infinity to +infinity. what we can do in order to see if this actually has an inverse is we can do what's called restricting the domain. And what this means is don't use everything, just use a part of it. So what I could do is I could just use the right half of this parabola. Right? So I could start here at 0 and go on to infinity. So instead of using everything in my parabola, let's start at 0 and go all the way to infinity. Because now this passes the vertical line test, so it's still a function, and it now passes the horizontal line test, which tells me it's 1-to-1, so I'm going to have an inverse. Right? So that tells me now that f of x actually has an inverse. Okay? So that should be our first step. If I walk up to you and hand you this equation and say, is this a function and does it have an inverse? Check your vertical line test to see if it's a function. Check your horizontal line test to see if it's 1-to-1. If both of those pass, then yes, it does have an inverse. All right. So now the next question is, how can we now find that inverse? Okay. That's where we're going to pick it up in part 2. So I'll see you there in just a minute.